Okay, one more video, last one for Class 1 and ME370. This is fall of 2021, a couple weeks before classes start. Let's see, August 3rd. And we want to try, I lumped this in because I really want people, I added this first week's class, or the first class of the semester, as a statics review after teaching the course a number of times and finding that people weren't strong in their statics. And then I kept adding topics, and when I saw people were struggling. And one of the main things, or amongst the things that I saw people struggling, was the concept of torque and where that torsion was taking place and what it even meant. So, and how to find it and where it was located, right? So let me, I start out with this little scenario of this intermediate gear, right? And this is a simplified one because I have the gear, the forces aligned. This one's aligned with the x-axis. This is aligned with the, in this case, the z-axis. I usually like to make that the y-axis, by the way. But anyway, I'll come back to this, but let me take a look at a real thing to start with. Okay, so I 3D printed a representative two-stage gear, right? So this, because we discussed it a lot, so it'd be nice to have one in our hands that we can hold. And so this is the input shaft, or at least I decided it was the input shaft. And you see we have a small gear right there, and it's got bearings and a little handle that I put onto there, and it drives this larger gear that's on this other shaft, which has two gears on it, right? There's this gear, which is larger than that gear, right? You can see that this one is small, that's large. And so when you have a small gear going to a large gear, the speed reduces, right? This one will move faster than that one. We could even prove that to ourselves, but we'll save that for another time. And then now there's another small gear on the same shaft, and it's driving this large gear on this output shaft. So in terms of terminology, input shaft, intermediate shaft, output shaft, right? So most of the problems, a lot of the problems I show will just be on an intermediate shaft. And the idea is that we've somehow driving this, maybe there's a motor connected over here instead of a handle, and that motor is driving this. So in between this handle and this gear, in here, there is torque, and that torque is being converted into a force right here at that gear tooth. And if I'm turning it in this direction, which is, let's see if I can show you. I'm turning in that direction. This gear is pushing downwards onto that tooth, right? Right. So there's wherever that gear is touching, or that's a lot of times. Well, some of the time there's actually two teeth that are touching two other teeth, but we'll get into that in the next class. ME370 is where we start talking about the specifics of gear design. But we need to know about these forces. This thing is transmitting a force. It's taking a torque that's in here. It has a force, and that force is being applied not only downwards, but there's a component that's coming inwards too. There's a radial and a tangential. The main one is the tangential. That's the one that's tangent to the circle that's pushing downwards. And just the consequence of the shape of the teeth, there's also a small component that's going towards the center, or radially, right? So that's moving this thing down, right? And so this thing is moving down, and then so there's this, that turns into, there's torque inside here. There's no torque out here because this thing is allowed to spin freely, but there's torque in here, and that torque gets transmitted through to this gear, right? So if this one is being pushed down right here by this gear, this one is pushing this gear down, right? So there's going to be a downward thing. So moving this out of the way, right? Moving that out of the way, this gear right here is pushing this guy down, right? and that's going to make this guy turn that way right there. So we can see which way the output goes, right? Now, we don't need to remember all of this, but I'm just giving you a narration of how this thing is working right here, okay? And so we see that the output is, yes, going that way. So this wing is coming downwards right here. This is, right? But if we're going to analyze this shaft, right, remember that this gear right here was pushing down on that gear. We know Newton's third law, equal and opposite. So actually, the tooth from this gear is pushing upwards on this right here. It's pushing upwards and a little bit inwards right there. So we have a force coming downwards on this gear and a force coming upwards on this gear, right? Remember, it's kind of weird. You have to remember, you have to kind of think it through, that this gear right here is pushing down on this output gear. But this output gear is pushing back up onto here, okay? And by the way, this is always for constant speed operation, right? So these are constant forces. So even though everything's moving, it's still a statics problem. If it starts accelerating, it becomes a dynamics problem. But as long as it's in constant velocity, constant rotational velocity right here, we're going to have a statics. It's in equilibrium. So it's still statically, we can still treat it as statics, right? Okay, so that's the part. But in terms of torque, the important thing is that this gear right here, this input that I'm turning here, is pushing down on here, right? And then torque is being transmitted through here to this gear, and this gear is pushing down in there. So the only place where there's torque is in between these two gears. And actually, that torque, if I had, I made them, but I didn't make them large enough. But this is something called a keyway that would go in there if I printed out these, like you can see, there's like a groove that's right there, and a little groove right there, and it's a little square, little piece that would fit in there. And you see, you would line them up, and then I would slip that little piece in there, and a very tight tolerance fit in there, and that would make sure that we're transmitting the torque right here. But I have it, they're not. There's no keyway in there, so they can actually slip. It's just the friction that's keeping them together right now. The plastic. Same thing would be true onto this one right there, right? So you could see that's where the keyways would go onto this piece. But anyway, the important thing here in looking at this is torque is only in between those two. So that's a full piece. And so you would see, well, here's a broken one. You could see that the torque is actually inside this shaft. And to be able to see something like a torque, or to see any of the forces or any of the moments, really, for the most part, you have to break the thing apart and be able to look on the inside, right? So that's like the big idea behind here. So let me grab my note sheet and take a look at this a little bit more closely. So in order to see torque, in order to calculate a torque, you need to cut the shaft apart. Right? We need to split the thing apart and look inside. And the way to do that is to make a free body diagram of just one of the things after we've cut it in. So as soon as we've cut it apart, we can see the torque, right? So you can see here's my little FBD, and I'm looking down the length of it, and I'm only looking at one of the two gears. And from that, I can find this torque. And that torque is going to be equal to this 5 kilonewtons times my 75 millimeters, right? So that's how that looks. 5 times 75 would give me, and Newton meters would be there. But equal and opposite, I could also have taken this other spot right there and taken a free body diagram and cut it there. And the best way I think to look at it is to look it down from the axis of the shaft. So we're looking right here at the cut, and we have 7.5 kilonewtons times my 50 millimeters. And if we multiply those, that would be equal to the torque right there as well. And they better be equal to each other, because this is equal and opposite, and it's inside the shaft. We've broken the thing apart and looked inside the shaft to be able to see that torque, right? So, this might be one way that we would find, like, we might not be given what this force was right here, right? And in terms of as a professor, I got to be careful that I label these things correctly, because if this force times this distance, 75 millimeters, doesn't equal this force times this, it's a dynamics problem. They don't balance out. They need to balance out. So I might not give you that force, right? That might be, so what you might want to do is now do a free body diagram of these both together, right? Now you can cut out the middleman right here by writing a free body diagram that looks like this right here. And one thing I left out of these, I didn't show the end supports of the bearings, but I'll leave those out there. And so what we could find is we could have a free body diagram that doesn't cut the shaft. If we don't cut the shaft, this force and this force, they need to balance each other. The sum of the moments need to balance out, right? That this 5 kilonewtons and this 7.5 kilonewtons right there, if we do the sum of the moments about this center point right here, if we say sum of the moments about the y-axis equals 0, we would say that's counterclockwise, therefore positive. We'd have 7.5, right? And that distance, the radius of the thing is 50 millimeters. I'll go ahead and make it 50 because it's kilonewtons in millimeters, right? And then this guy is negative because he's clockwise. And it's 75. And says equal to 0. You notice there's no unknowns. This better be equal to 0, right? So we could prove that to ourselves. 7.5 times 50 is equal to 5 times 75, right? So, now we said that equal to 0. There was no unknowns here, but we did demonstrate that they were equal to 0. What many students will do is they'll put a torque in there, right? They'll draw the torque in there and they'll label it, and then maybe they put this in here and they find the torque is equal to 0. That's not true. The torque is only inside the shaft. It's internal to the thing. So don't do that, right? Just take one or the other in order and do one of these diagrams with the shaft cut in order to see that. Now, one of the classes I taught at one point used a torsion diagram. I don't think they teach mechanics. I don't think they do that in the mechanics and materials here. I think maybe if you went into your Beer-Johnston book for mechanics and materials, you would. I think they do it. The book I used in teaching mechanics and materials one year was Philpott, and he did do a torsional diagram. But I kind of shy away from doing that because if you haven't been introduced to the torsion diagram, there isn't necessarily a reason to do the thing. I think I actually prefer just to do individual diagrams like these, like one of these, to be able to do it. So like if you had something more complicated like this one below, I would do that. So I'll demonstrate that here in a second. But the torsional diagram, if I can recall correctly, it just shows the torque in between each of the shafts, and I think they're taking a left to right approach. And I'm trying to decide which is positive right here, whether it's clockwise or counterclockwise, and whether you're cutting the shaft in a particular location. I don't know if it's any beneficial, but the idea right here in the terms of the torsional diagram is that you would have something along those lines. And I don't think I wrote down what these are, but what is 50 times 7.5? 50 times 7.5. Boom, you get 375. So it's 375 Newton meters is the value right here, and that's the value all the way along. We also, by the way, we ignore that the gear actually has a thickness and just go from the center line of it, even if that's not exactly true from how that's distributed. But that's what we do. We say in between these two gears is 375. So if we take like a more complicated scenario going on right here, where we have 160 Newton meters going that direction, 380 newton meters going this direction, 330 newton meters going this direction. What is the torque that's on this other piece right here to have equilibrium? If the thing is going at a constant angular speed, it has to be in equilibrium. And we don't even know for sure that that arrow is correct, even though I think I took this from a problem where it was. So we could approach this in a bunch of different ways. The best way I think you could do is to like cut these shafts, right? To look at the thing, or to combine them all together. So in this case right here, one method that I would suggest, I'm going to draw, we don't know, we're only given torques right in here. So I'm going to draw them as different sizes. I'm going to make C the biggest, okay? So I'm going to draw that out right here. And so we have 380 newton meters right here. B is going to be the next biggest. And that's going to have 330. I'm going to leave off the units because I didn't have enough room. I'm going to make D the next biggest. And that's 160. And then lastly, it's going to be smaller than it really is right there. We'll make that A. And because the arrow is already drawn that way, I'm going to draw it that way. And I'm going to write TA right in there. Didn't make my diagram big enough. But anyway, so if we take the sum of the moments about the x-axis, and I'm going to look down this way right here. I think that's what I did. Yeah, that's how I drew it, right? Yep. All we have to do is, and then say that that is what we consider positive. We have to choose something as positive. So I decided counterclockwise from this view is going to be positive. And so I said that we have negative 380 plus 330 plus 160 and then minus TA. Minus TA equals 0. We would find that TA is equal to, let me see. I'll bring that TA over to the side in my head. So I'm going to take this and go 380, make that negative, and I go 330 and add it, and 160 and add it, and I get 110. And I get a positive value, which tells me my guess, the guessed direction was correct, right? That's one way that you can approach the thing. You guess a direction. If you get a positive answer, you guessed correctly, right? And so that's one way that we can approach it. If I was going to instead draw out and do that diagram method, and I would do something along the lines of this right here, right? And I would draw, this is where my torque is going to be, and nothing happens. There's no torque in the shaft in between here, right? So this one is, we'll say that it's counterclockwise, right? So we, in terms of our international right-hand rule, putting our thumb in the direction of the positive x-axis, it's moving along that way right there. So we're going to say that this is a positive value of 160 newton meters. Now this is 380, and it's going counterclockwise, so it's negative. So we would subtract out. So we go 160 minus 380, and we get a negative 220. Right? That means the torque in between here and here is 160. How would we know that? Because if we cut this thing, right there, right? And okay, so here's the end with the bearing onto the thing, and we were to cut, and here's the internal torque that's taking place. I should actually draw it the other direction right there. So we have 160 onto that thing. We'd have a torque that needed to balance out in between, like cutting right there. That would be the internal torque, so that's why that has to be 160. Now, if you wanted to do the same thing right here, I need another piece of paper over to the side. Maybe I'll use this down here. If I wanted to now instead confirm that that's 220, what I would do is I would cut right there, and I would draw out a free body diagram that looks like, oh, that's not a very good gear. And here's where I'm cutting right in there. And so there would be a torque right in there. So this guy right here, he is our 160. And this guy right here, here's our 380. So we would end up having to find probably this torque right here that we might call torque BC maybe. That would be, right, this guy right here needs to balance out that one and that one. And so that's what's telling us that this right here has to be 220 right in there to be able to balance out the torque that's applied to here and the torque that's applied to here. Now, when we keep going, this guy has a positive, because he's clockwise, 330. So we would add 330 to our negative 220, and we end up with a positive 110. So in between these two shafts is 110, and it needs to go to 0 here at the bearing, and therefore there's 110 Newton meters applied to this guy right there. And which direction does it need to be? Well, this is positive, so this is counterclockwise. So this needs to be clockwise in order to get negative and to bring it back down there. So there's a way to think your way through what's going on in the torques and the torsion that's happening. Torsion is a important loading condition that we're going to look at when it comes to stresses. So these are the internal loads, and we'll talk about review some stress stuff in class 2. Hopefully these videos will be helpful to people who that are having a little difficulty recalling the stuff that from statics that we need for this class. So thank you, and there was a lot of video.